Well, good afternoon, everyone, and welcome to this webinar on best practice for heat pumps in aquatic centres. My name is Jared Leake, and I'm the CEO of A2EP, and I'll be hosting this webinar for you this afternoon. I'd like to begin by acknowledging the traditional custodians of the country throughout Australia and their connection to land, sea, and community. And I would like to pay our respects to their elders, past, present, and into the future. For those of you who are new to A2EP, we are a member-funded non-for-profit organisation that works with these fantastic companies shown here now to improve energy productivity through Australia. We do this by connecting researchers, governments, manufacturers, all sorts of end users with technologies and energy consultants. We advocate for good policy which helps improve energy productivity and reduce emissions, and we explore the world for best practice in terms of energy productivity and decarbonisation technologies. And this webinar here today is brought to you by Sustainability Victoria. We'd like to thank them for sponsoring this webinar, as well as our members who also support us with bringing this to you today. Just a little bit of housekeeping to get us started. To let you all know, this webinar is being recorded and the slides will be sent out to you early next week. As you come in and out, this is a webinar where you can come and talk and ask questions, and we certainly encourage that today, but we do ask you to stay muted and keep your camera off during the duration of the webinar. So we're hoping to have questions and answers after each of the presenters. We've got some fantastic presenters here for you today, and they're really keen on an interactive discussion. So we'll do a Q&A after each presentation, but if we run out of time, they'll continue that in the chat box afterwards. If you do have a question, please feel free to use that raise hand function there at the bottom of what you'll see on the Zoom screen, and we'll try and use that to triage who should be getting their question asked and what we should answer. The other thing to say is we've got a 2-hour webinar, so we thought it'd be appropriate if we just have that 5-minute break halfway through, just so you can top up your cup of tea. Okay, so we have a great lineup for you this afternoon. We're going to take you through a really good journey and tell the story about how to implement best practice for heat pumps in an aquatic centre. I'll be kicking things off with Chris Warris from Northmore Gordon is going to help me with an introduction here. We'll step through a few ways of improving the return on investment for heat pumps. First of all, we're going to talk about building and comfort, and we've got building scientist Noe Hildebrand taking us through that. After that, we have a great little recent case study that's been done, funded by the ECA, by Derek Harbison and his team at Negawatts. They're going to present the findings of that, and it's quite an eye-opener of what's possible in terms of energy savings. We'll then be hearing from Dr. Jean-Jean Duverge, who's done a PhD in aquatic centres and energy and water usage, and Jonathan will be taking us through how to understand that heat demand and really model the amount of heats required for an aquatic centre. Step 3 we'll look at for improving that return on investment is right sizing of the heat pump. And to do that, we have Tony Kimpton joining us as the ex-managing director of GEA Refrigeration, who knows a lot about heat pumps, and he'll be able to take us through the steps that you need to do. Finally, we'll be going back to Chris Warris from Northmore Gordon to take us through grants and just that financial case comparison between heat pumps and boilers. And then I will also give a bit of a summary at the very end here on maintenance and operations of existing heat pump installations at aquatic centres. Share with you just a little bit of research we've been doing on that one. Okay. So let's get into things. And joining me there at the moment is Chris Warris. Chris, are you there?
Yep. Here, Jared. Happy to be here.
Thanks for joining us, Chris. And you're the principal energy consultant for Northmore Gordon. Chris, you've done a lot of audits and studies for aquatic centres over the years. I think you would have seen things change a fair bit over the last few years with increasing gas prices and reducing electricity from solar PV.
Yeah, that's right. I mean, increasing gas prices are a real driver for sites to get off gas, but also decarbonisation plans. A lot of organisations have net zero plans, and to achieve net zero, you have to get off gas at some point, and heat pumps are a way to do that.
Absolutely, but to do that, it's not just a matter of that fuel switching, is it? This is a typical sort of pyramid way or sequence of how to do that decarbonisation. Very typical, I guess you'd see this, Chris, in your energy consulting life, using this a lot, this sort of thing at the moment. Why don't you just take us through this sort of concepts here?
Yeah, so I mean, we always recommend that sites try and do what you can to reduce your energy consumption with the energy efficiency as much as you can. And that can reduce the demand on your heating systems as well. So then you can put in a smaller heating plant that reduces the cost, makes the business case better. So do those on-site opportunities as much as you can, and then that reduces the amount of renewable electricity you have to buy from the grid, and the amount of carbon offsets you would have to buy at the end for your net zero strategy, which just costs you money. So yeah. Do those cheap and easy things first and the expensive things later.
Absolutely, and I think we'll see that messaging coming through all through this webinar today. What I thought would be worthwhile kicking off is just talk about a little bit about some of the myths that seem to go around about heat pumps. It's not a new technology. I mean, most people have a heat pump in their home in terms of a reverse cycle air conditioner, and so people are familiar with it. And they have been used in different cases and different industries over the years, and some successfully, some not so. I thought, let's just run through a couple of myths that we come across when we're talking about heat pumps. I think, Chris, you probably would have heard some of these as well. The first one that we hear probably the most often is that heat pumps don't work in cold climates. Now, this is certainly not the case. They do indeed get lower performance compared to when the ambient air is warmer, when you've got an air sourced heat pump, but they still do work. You do need to size them for that colder temperature, for that colder weather, because they still indeed do work even below 0 degrees. And if you look at the reports from the likes of the IEA, you'll see that Sweden and Germany, they have the largest number of heat pumps installations anywhere in the world. Chris, I think you've been following those heat pumps installations over there as well.
Yeah, and the reason they can do them effectively in the cold climates is that they cleverly use as much heat recovery as they can as well. So rather than trying to source heat from sub-zero air, even though it can work, it's much better to try and recover exhausted heat from the building or from a warm water source somewhere. And they make very good use of that. And in those situations, even in a cold climate, a heat pump can work very well.
That's right. And here's a case here. So there is a this CO2 based heat pump down in Perisher, in the Snowy Mountains within Australia, and this one is providing, I believe it's just domestic hot water for this Matterhorn Lodge there, and that's been installed for a few years now and working and doing the job for them right through winter. So absolutely can be used in cold climates. Next one we hear a bit is heat pumps are expensive, and it certainly is a case that on a like for like kilowatt basis, they are more expensive than your incumbent technology, like a gas boiler or gas hot water generator. But this is part of our main message here today. If you're doing a like for like change, probably doing it wrong. And just to explain that further, if you've got, say, a 1 megawatt steam boiler or 1 megawatt hot water generator, when you're replacing that with a heat pump, if you're looking at the reduced heat losses and looking at sizing this correctly whether it be with thermal storage and making it perform and take out the peaks using thermal storage, your heat pump should be a lot lower. And in this example we have shown here, it's and we've seen that in various studies, a 1 megawatt boiler can regularly be replaced with a 500 kilowatt heat pump and, say, with a thermal battery. So if you're doing it like for like, definitely doing it wrong, and it's definitely going to be expensive. Myth number 3, heat pumps don't reduce emissions. Now, that is the case, but only sometimes. If you looked at a worst case scenario, the middle of winter, where the performance of the heat pump is not so good, and then you're looking at right now with a high CO2 grid emissions intensity, the likes of Victoria, where they're burning a lot of brown coal, and maybe that's 1 tonne of CO2 per megawatt hour. In which case, in certain cases, when there's very cold and very poor heat pump performance, yes, you would not be reducing emissions. However, as you see on the graph here on the right, with the federal government effectively adopting the step change scenario for reducing emissions on our grid electricity network, the grid intensity is coming down and going to come down fast. The target is for that 83% reduction, or sorry, 83% renewables, my mistake, by 2030. And so you'll see this grid emissions intensity come down really very quickly. And so it's somewhere around about maybe 2025 or so, 26, that you'll definitely, no two ways about it, virtually at every point in time, you'll be getting reduced emissions. But I'll make the point, we can't all change in 2025, 26. We need to get going now. Very similar to EVs, electric vehicles. We can't all change in 2026. We need to get going now. So we get to the situation of heat pumps, and are they appropriate for aquatic centres? And this was the question which was asked by some of the first movers within Victoria some 2 or 3 years ago, and they turned to existing heat pump installations at aquatic centres throughout the world. And here's one case: the likes of Brimbank Council, when they were considering this at St Albans, turned to this case here in Timaru in New Zealand. And they saw very quickly, hey, in Melbourne, average July temperatures 7 to 15 degrees. In Timaru down there in the South Island, -1 to 11 degrees. So they've immediately said, tick, yes, this technology is appropriate, and let's explore this further. And so they are one of 4 major aquatic centre upgrades which is going on right now, and each of them are actually doing it slightly differently. So there'll be a lot of lessons learned coming from this. We have Cardinia there in Geelong looking at doing a hybrid heat pump combined with a bit of gas boosting. Northcote are doing a air sourced heat pump, but ventilation, heat recovery, and a lot of building, and really airtight building, strong building they're looking at there. St Albans, I understand they're using several smaller heat pumps, this HFO type, as well as thermal storage. And then finally understand that Collingwood is planning to use a CO2 heat pumps, possibly for their domestic hot water, and a low charge ammonia for their pool and space heating. But that is under design review and still to be confirmed, I understand. And apparently there is others as well, but these are the major ones that we've got most information on. So this is where it's at, and so a really exciting period over the next few years to make sure the lessons are learnt from these projects and really get some sharing going. But meanwhile, Chris, let me throw back to you, and if you could take us through this idea of not doing things like for like. It'd be great to give a bit of an overview on that and compare this to a boiler.
Yeah, so as Jared mentioned, replacing like for like is the easy way to do it, but it's going to be expensive. And the speakers to come are going to explain how to size it correctly and how to reduce your heating demand so that you can put in a smaller heat pump and still get the same water temperature that you need. So you've got a few options. You can do the like for like capacity heat pump. It's going to have high capital and be a long payback. What we often find though is that because gas boilers are relatively cheap, they're often oversized. They're just over-designed to have 50% extra or 100% extra capacity just in case. And you can do that when you've got a cheap boiler. You just can't afford to do that with heat pumps because the capital cost is higher. So if you look at the heat load properly, or either model it or look at the actual data from your existing heating plant, and then correctly size the heat pump to meet that demand, you can often put in a much smaller, sometimes half the size. And that'll give you a much better payback. It'll reduce the capital, improve the payback. 10 years is typical of what we see from that, as opposed to, often over 20 years if you're doing a like-for-like replacement. The other thing you can do to improve the performance and reduce the size needed for your heat pump is to try and do some heat recovery. So aquatic centres are often quite warm inside and with a lot of fresh air to get rid of the chlorine. And all that heat is just escaping to atmosphere. The magic of heat pumps is that you can actually capture that heat and reuse it, upgrade it, and put it back into your facility. And so you need a smaller system again. So if you can do that, that significantly improves the payback. And then if you can combine that with some energy efficiency, to reduce, improve the building fabric, so that your facility needs less heating overall, you can reduce the size again, and combine that with some grant funding from the Victorian Energy Efficiency certificates, which I'll talk about later. You can see that you can really get these down to less than 5-year payback by doing all those things correctly. So yes, so don't do the like-for-like capacity heat replacement. If nothing else, at least size it correctly. And then ideally, if you can, try and incorporate some heat recovery and some energy efficiency as well.
Yeah, Chris, we're really looking at a dramatic difference there. You're saying greater than 20 years. If I've just got that 1 megawatt a steam boiler, I go to replace it with a 1 megawatt capacity heat pump. That's going to be around 20 years. But if I take these steps, I'm getting down below 5 years.
Totally possible, and certainly with increasing gas prices as well, those paybacks come down even further. So we were used to having gas at $10 a gigajoule or less, but at the moment it's $40 a gigajoule. So if you use $40 a gigajoule, the paybacks become almost no-brainers.
Good one.
So yes, the key messages that we're going to repeat through this webinar in a bit more detail is size the heat pump correctly. Your existing gas boilers are probably oversized, so you need to understand your actual heating demands, whether that be measuring your existing system or modelling it properly. Use the waste heat from your facility where you can to improve the heat pump performance. And using heat pumps and getting rid of your gas heating. If you can eliminate your need for gas, that de-risks you from volatile and increasing gas prices, which we are expecting to be and to remain high over the foreseeable future. And then finally, access additional funding through the Victorian Energy Efficiency certificates. So these are the key messages we're going to elaborate on a bit more.
Many thanks, Chris. Thanks for helping me kick this off. And you'll be back joining us later and go through some of those paybacks in a little bit more detail and a few more calculations behind that. So look forward to you joining us later. Many thanks, Chris.
Thank you.
So we thought let's take a step back now. Now we've got a bit of a pathway of how do we go forward. Let's talk about some of the fundamentals of what we're trying to achieve here. And to talk about that today, I've got Noy Hildebrand, the Principal Consultant from Revitalising Environments, joining us here today. Noy is an architect and a building scientist, and she is absolutely passionate about how to design a building efficiently and making sure it's all energy efficient and the requirements for that. So absolute pleasure to have Noy joining us here today. Noy, if I could get you to start sharing your screen and start your presentation, that'd be much appreciated.
I really like chewing on problems with complex and competing requirements, which is why aquatic centers is such a fun one for me. This little image is just some research I've done on natural ventilation, so sort of low energy cooling. Useful in this case, but not directly. Slides. Okay. So first, what does a high-performing aquatic center look and feel like? This is kind of more just a brainstorm, but can you imagine an aquatic center that's delightful to experience, very pleasant, supports occupant health for different user types, is relatively low maintenance, connects people, community to place, ecology, and where energy savings pays for part of the added capital costs. Yes, it will cost more. If you have an idea for what your kind of high-performing ideal aquatic center would look like, please feel free to drop it in the chat. I'm always open to ideas. These images are from St. Sidwell's Point, which is the new Passive House Aquatic Center in Exeter in the UK. So some options for decarbonizing aquatics Jared said, one of the options is to shut down pools, and some cities in Germany are doing that. Some places are also turning off pool heating, so people can go swimming if they want to practice, getting bold and brave in the pool. The other is to trial lower heating set points and changing up lowering ventilation rates to reduce operational energy use. That won't remove all of your issues, but you can at least see what the lower limits are if you have an existing building. And third is to make your pool halls more comfortable and much more efficient via design and equipment changes. Yes, you've heard heat pumps and boilers are not equivalent. You can't swap them over. So it's kind of our gassy habits versus our aspirations to decarbonize. What's going to happen? Well, first I thought I'd share a pathway to decarbonization. Now you can do things in the wrong order here, but when you do things in the wrong order, it's really, really expensive, as I'm sure some of you have discovered. So you start with your typical building. You apply design adjustments that will lower its energy use. So in this case, the picture shows external window shading and less window area, but it can, other things can be like insulation and also more efficient building services design. Once it's as low energy as you can design it to be passively, then you go into switching out the equipment to be electric. And then it's only after that that solar PV you can make the most bang for your buck for solar PV. So why do pools guzzle energy? I like to think of it as heat debt, like they're always catching up, they're always behind. So a heated pool will lose energy mostly by convection and evaporation. Predominantly it's evaporation, but with more convection, the evaporation can also increase. So eventually what happens is the pool water is heating the surrounding air. And when it's more windy, like I said, more heat loss. We're not going to go through all the formulas for heat transfer here, but suffice to say that the key variables involved are the change in air temperature between the air and the water temperature, the pool surface area, the air speed, relative humidity, and emissivity that connects to radiation. So business as usual pools, sometimes I like to call them glorified tents. I think you will see an example of this in some later presentations. But yeah, indoor pools are good because they do use less heat than outdoor pools, but how much really depends on the quality of the enclosure and equipment. The water vapor usually lingers inside and it condenses on cold surfaces like window frames. And so much of the issues have to do with managing condensation. So the equipment often runs 24/7 in order to maintain water quality and also to address condensation. And since it's on 24/7 often, that's probably why it guzzles energy. Here's an example of one of those. This is an aquatic center that had an air tightness specification, but failed at the air tightness testing phase. This is its roof, a photographic and a thermographic image. You can see the light colors are the warmer colors and the darker colors are the cooler colors. You can see that the parapet is bleeding heat. And inside the parapet wall, this is what it looks like. It's condensing. So this is interstitial condensation. So it would never be observed if somebody didn't go peeking inside. And even though this building's only a few years old, it's already moldy. So it doesn't take much for a heavily conditioned building like this to have really major mold and moisture problems. So the next step would be to start looking at your building fabric. So what is a high performance building fabric? High performance building fabric delivers outstanding results and environments for its occupants with minimal net energy use and other inputs required. You can think of it a little bit like the way you think of your clothing ensemble. I put some images there. For aquatics, this starts with a continuous, well-insulated and airtight enclosure. Why is this important? Well, a building enclosure has to cope with a really wide range of natural forces. That's right, forces of nature with competing demands. Those are listed there. A building enclosure is also the largest building system. It's the largest surface area and it can lose a lot of heat because of that. And finally, related to the building enclosure, glazing is linked with major heat and glare issues. And for a pool, glare issues can be linked to safety issues. Windows are always going to be thermally weaker than an insulated wall, so a bit like a hole in the bucket. So it's really important to limit your glass and frame area. Now, so we've covered indoor pools. We've said the continuous well-insulated building fabric is really important because it slows down the heat loss, reduces condensation risk. Finally, if you add ventilation with heat recovery, this can be hugely beneficial as well. And on that, this diagram kind of describes why that is. Not only why the heat recovery is beneficial, but the importance of that building fabric. So in this diagram, the inputs are on the top and the outputs are on the bottom. And the outputs are to save energy. You can see how everything is super dependent on those green boxes, which are the high performance fabric. And they're really key to unlocking those three outputs of reduced air handling demand, reduced pool water heating demand, and reduced space heating demand. And the other thing you can see is that the recirculation, there's all these other things that are related to, can you see my mouse? Can somebody tell me if you see my mouse? Great. You can also see that these other things are related to, there's all these loops that we put ourselves through to address the condensation. It's like the hairdryer approach. The humidity doesn't go away. You're just making it look invisible. But that was a standard approach for a long time and still is for some. So what do we do next? So here's some of the tips and ideas for new buildings. It's really just a list, but it's really important to have a compact geometry. So think of it as a lower surface area to volume ratio. You can kind of keep your ceilings low, separate rooms of different temperatures, really separate, like really separate them, not like, oh, it's only 2 degrees, we can just share the air. Yeah, don't do that. Just assume, early design is probably good to assume a really thick insulation. You can always reduce it later. I've said the surface area one already. Really limit your glazing area. Avoid horizontal skylights if you can. And address all types of thermal bridging and air tightness. Think about air tightness early. Now, of course, it changes a lot if you're retrofitting. Often retrofitting is thought of as the too hard basket, and that is partly true. But the key to this is having a smart and experienced team who get along and who are just, kind of can communicate really effectively together. It's probably really, I think existing buildings are interesting because you can kind of apply a science experiment approach. You can like survey and measure thermal comfort and ventilation. You can do air tightness testing to find your leaks. Remember, if you do seal up leaks, you do it from the inside. So you want to protect your structure from that humid air. And you also don't want to remove operability of windows and doors, not all of them at least, because you want to be able to have adjustability for summer or for certain conditions. How am I doing for time? Okay, it's almost done anyway. Really assess your glazing areas, and where possible, you can reduce those glazing areas. It's really important, especially for skylights. Find your thermal bridges, reduce their impact. You can do that pretty much with a thermal camera, but also with kind of like other types of thermometers. Again, separate your zones if you can, and with professional help, retrofit insulation. I say that because there can be moisture issues that start to happen with retrofit insulation. That's pretty much it from me today. Questions?
Thank you so much, Noi. I'll see if anyone's coming off mute or would like to ask. We've got time for, say, one question. Could we keep you just for another few minutes for one question then, Noi? Yeah. Let's see if any questions comes through on the chat. A question here from Alexia Morgan from Belgravia Leisure. Thanks, Alexia. Can you double or triple glaze to reduce heat loss, but still gain the advantages of skylights, natural light, to reduce any electricity consumption for lighting? So,
it's not, while you don't, I wouldn't say you should never use skylights, but what happens is, let's say, I'm going to use demonstration. Let's say this is your double glazing. If it's like this, if it's upright, one side's gonna be cold, one side's gonna be hot. And
can't see you.
oh, you can't, can you see me?
Oh, I can see the yeah, there we go.
Can you see me now? Oh, I can't, I don't know where my screens are. Okay,
Gotcha.
can you see me now? I can see, okay. So this is your double glazing. One side's cold, one side's hot. And when heat tries to transfer, it has that air gap that kind of resists that transfer, and that's really good. And if it gets, you have a little bit of conduction inside, but if it's small enough, if it's narrow enough, you don't have much, convection, sorry. So you don't have much convection inside, it's mostly conduction. And convection is just that, when it circulates. But when you have the same high performance window and it's horizontal, and your cold side's on top and your warm side's below, anything that's warm rises to the top, gets cold, circulates down, and starts to circulate. So you have these little convection loops inside your double glazing, the space between your two pieces of glass. So what that just means is that the same glazing performs less well. And so if you think about it in terms of you're getting your money's worth, if you're paying like say $1,000 for it, you're only getting like $400 worth. Does that make sense? You can do it, it's expensive. Probably helpful to think of glazing a bit like crown jewels or something, where it's really, you get the good stuff, expensive and special.
With the cost of LEDs, would you be then saying, well, you're better off, and maybe you've done the calculations to say better off taking away that skylight, and that's natural light, but putting in LEDs now because they're such low electricity consumption?
Are you thinking of a retrofit or no?
Retrofit. Let's talk retrofit. I think that's what most people will be going through.
So for retrofit, I would say if you are I would say don't get rid of all of it necessarily, just because if it's already there. But I would definitely say that you want to almost sandwich it with other things to kind of really isolate that you almost need to add stuff to make it have higher R value. So you probably don't want to have it all over the place because you're bleeding heat, right?
Yep.
And but I do see value in daylight, and LEDs, while efficient and great in terms of low energy use, and they can have okay color rendition. I think it's important to also have moments where you can see what the sky is doing, what's like outside, and that kind of connection to the outdoors and nature. I think it's important. I don't think it's more important than going off gas, but I don't think that it's an either or. I think that you can, if you kind of manage it right, you can have a little bit of both.
Gotcha. Thanks.
Personal opinion. Some people don't care for daylight. I do.
Thank you so much, Noi. And we do need to keep moving. And maybe if you've got another couple of minutes, there's a question there in the chat there already coming in there from Rani. Maybe you've got a minute or two to answer that. At the very least, we'll capture all these questions and we'll try and get answers published for them anyway. But I would like us to keep moving. And our next presenter today is I thought we'd hear about some really practical on the ground what's happening here. And Energy Consumers Australia funded with A2EP and Negawatts, Derek Harbison from Negawatts, to do some studies on swim schools and look at their energy performance. And to say that we're blown away by some of the results is an understatement. It was a fabulous little study done very quickly and with some great information. And we did it right at the right time of the year there, didn't you, Derek, there with winter. Derek, if I could get you to share your screen and take us through the results of your study and what you found. Get you to come off mute there, Derek. And get you to go into presentation mode and we'll be away. I think you might still be on mute there, Derek.
Saying I'm off mute, but you hear me?
Got you now.
Okay. Thanks, Jared. Thanks for having me along today. I'm Derek Harbison from Negawatt Projects. I won't give too much of a presentation because I've spoken to a lot of people in this group before, or an introduction. The aim of this was to look at a very small group of swim schools. We started off trying to look at 3, but COVID intervened on that. And the first thing we did, we were looking at a swim school group in Victoria, which has at the moment 12 pools, which is expanding to 15 in the next couple of months. And we were using the metric energy use intensity, which is kilowatt hours per square metre per year. So we're using that as our benchmark to basically compare apples to apples. That's what this looks like. The reason we got so sort of embedded in that number was we have a lot of similarity on the right-hand side of the chart. Hoppers Crossing has insulated walls. Carrum Downs is sort of the midpoint, so we chose that one, and that's also in the middle of an upgrade, which we'll talk about in a moment. And then Fit to Swim in Sydney, as you can see, is just a ridiculous number. And we wanted to work out why that centre is just such a low figure compared to the others. So we got some money from Energy Consumers Australia, and A2EP assisted us with getting ourselves organised with a few elements, and we're up and away. So we'll look at two centres. This one, most of these swim schools we come to, essentially, they're industrial shed, and they leak heat like no tomorrow. So they have a lot of problems with condensation, with just energy bills. A centre like this will usually have, this is a 25 metre by 4 lane pool. They'll usually have a bill sort of northwards of 100,000 a year, just to give you some rough figures. This is an older centre, but it's still pretty typical of a lot of pools we see in the market. So this is being recorded. So I said, if you need to see some more accurate figures on this, the other thing is they can't control the temperature in summer. This pool just keeps climbing in summer. If it's a 45-degree day, which they're forecasting down the track, we're going to get some extreme weather events. This pool will be unusable on a hot day. Now, Fit to Swim's, the council made them build it to look like a house. It's in a residential area. It has a school, that's a school crossing, so it has a school across the road. They're able to control the temperature and the humidity in the room very tightly. So on a warm day, it's 29 degrees, and on a cool day, it's 27 degrees. And they stay within that range. And the ceiling and the walls are both insulated panels. And this is the lowest recorded energy usage we've seen of any centre in Australia by a long shot, in fact, by about 300%. So that's, you can see it looks like a house. It has solar panels on the roof, and it has 2 heat pumps. So the thing that came up in the data, first of all, is one of the heat pumps wasn't working, or at least wasn't operating on the energy, the power consumption metering that we were putting on. And that was the first indication that something was, needed more investigation. This is the air handling unit. It's an arm core unit, which is pretty typical of these sorts of air handling units, where we've basically got outside fresh air being brought in at 100% and then exhausted out of the building. When the heating coil's on, we get reheat recovered, and when it's not on, you're just blowing around warm air from the building. These are the typical semi-hermetic compressors that we're seeing in the units. This is a single compressor unit, and it's about 1,500 litres per second that's being transferred in and out of the building. Now, there's a couple of rules of engagement. The neighbours don't like it when the air handling unit comes on, so they have to turn it off at 8 o'clock at night and switch it back on at 6 a.m. And that was actually advantageous for the centre, because it forced us to look at what happened to the centre when this system reacted to that turning on and turning off. And the other thing that happens is there's a peak time in the afternoon. That's when the kids are finished school, piling into the swim lessons. And there might be 80 or 90 people in this room doing swim lessons at a time. So here's the first data that we got through, which is showing that first block on the left-hand side that you can see. We're talking the wriggly line at the bottom now. That first block is the air handling unit trying to adjust the air at 5:50 in the morning, and it runs and heats continuously until about 9 o'clock, where it goes into a bit of a modulating mode. That second line you can see on the right-hand side that's higher up, that's the heat pump. It only runs between, say, 12:30 and 9 o'clock at night. Just one heat pump, and this is in the depths of winter. We then added in a temperature and humidity monitor, and that's when the fun really starts. You can see on the left-hand side at the top, that humidity line, it just keeps climbing at night. It gets well above 70% humidity, and that's because we have to just turn the system off. It's got a pool cover on, but the system goes off, the temperature's dropping away. As soon as the air handling unit comes on, it basically inverts that the climb, so our humidity drops, the temperature rises, and it overcompensates. And the rest of the time between sort of, what time are we, about 6:30 or so, 7 o'clock, we've now got this downward slide until the system sort of balances itself. We say it's in stasis. You'll see a little swap over there. That's swim classes starting, and you'll see this big bump in the humidity and the temperature. Now, the takeaway from this is you have to measure the data in these centres. Until you really get down to the bones of what's there, you're just guessing. Some engineers will just take some numbers for the size of the room and give you a formula and say that's how big the unit has to be. But until you've really started to look at the data that's there, you're flying blind. All right, so let's have a quick look now at Carrum Downs. As we said before, this is what it looks like. It's pretty dark and dingy. The light in here is, from memory, I think it was about 80 lumens. So it's about 1/4 of where it should be for lighting for this sort of facility. And the windows at this stage were bleeding heat. And the roof, there's insulation on the roof, but basically it's tin with about, 15 millimeters of insulation blanket. We replaced the windows. We replaced 3 windows with double glazed units. There's a bit of a story to them, but we won't go into that now. The units, that window unit is around about $4,000. So double glazing is super expensive when you compare it to other treatments. The windows on the left, as you can see, there's a single glazed window with a louver above it. In summer, when it's hot, they open the louvers and try and solve their heat problem. On some of the windows, instead of double glazing, we just cover the windows over. We put some insulation in behind. We put some core fluid first against the glass, then some insulation, then a fiberglass panel. To cover that window in entirety for materials is $300 compared to $4,000 for a double glazed unit. So there's nothing wrong with covering a window. As we point out to everyone, this is an educational facility. They're learning to swim. They're not there to look at cars in the car park. So there's nothing wrong with them, or at least there's no complaints from anyone in the building saying, gee, we really need to see the car in the car park compared to a covered window. Now, we covered the windows, and this was the next real surprise to us. Stuart Nesbitt famously said to me at Coburg, he said, we covered some windows and we had a 30% reduction. I thought, it can't be that much. It is. He was 100% right. There it is. There's your drop in gas consumption. We shaved 1/3 of the gas consumption off, just covering 11 windows and replacing 3 with double glazed units. We still have 4 more windows to replace. But again, it's critical that you measure the change in this before you make any more upgrades. And there's some ducting on the right-hand side at Fit to Swim. That's what an insulated ceiling with ducting will look like on the left-hand side of the existing building. So this is the process we've ended up with all of the upgrades now. You learn from these upgrades as you go along. First of all, we're going to collect data. We're going to look at the M&V rebate available, do a calculation for that. We have to have that started before we do any work in execution. We added monitoring equipment. So we're looking at energy consumption, temperature, humidity. We have to look at the roof analysis, because if we're adding insulated panels to ceilings or we're putting on solar panels, the roof has to take it. There's no point putting this in and finding your roof collapses or is at risk of collapsing. You'll be in trouble. Then we go over to the execution side. We're going to insulate and then measure the building. We're going to upgrade the air handling unit and measure the building. Then we're going to go to the heat pumps, which we're about to do at Carrum Downs now. The heat pumps now, from the initial quotes we had and from engineering, they're about 1/4 the size. So again, the lesson is, if you're measuring and taking your step through this and really looking at the information to work out what's going on, you'll probably find you're spending less on plant that's there. And then finally, when this system is fully running for a few months, we'll look at the solar system and see what size solar system goes on. And Jared, that's just about does me.
Thanks very much, Derek. And we've got a lot of people here with much bigger, obviously, aquatic centres, but I think some of the same principles apply, and you've really reinforced that message from Noi there of looking closely at that, at the amount of glazing that you do have. But also, having that data as well to show that you've moved on. Thank you so much, Derek. If there's some questions for Derek, please pop them in the chat and he'll be able to answer those. He'll be with us throughout the afternoon as well. I am just a few minutes behind schedule, and I do want to have a short break there coming up at 3:30. So I'd like us to move on, and I'll ask Derek to stop sharing, and we'll get our next speaker to start sharing for their presentation. Next person we have is Dr. Jonathan Duverger. He's a director of Northern Environmental Design, and he has spent many years doing a PhD for aquatic centres. And I can tell you, and we started doing some investigations here about 3 years ago. We noticed when we searched globally, there really has not been many studies, proper in energy and water studies for aquatic centres. And we were so delighted when we found one, and then even more delighted to think it's actually in our own backyard here in Melbourne. So I'd like you to, if you could welcome Dr. Duverger to take us through buildings and how to size the understanding the heat demand from them, and share lots of learnings he's had from his PhD. Jonathan, over to you.
Okay,
Yeah,
let me share my screen. Yep. Okay, can everyone see my screen?
We got it. Go for it.
All good. Okay. Yeah, so my name is Jonathan Duverger. I'm an ESD mechanical engineer. So I've been in the built environment for about 13 years, looking at different types of buildings, doing ESD consulting. And as Jared mentioned, I actually did a PhD a couple of years ago on energy performance and water use of aquatic center, actually in Victoria. So, and I also publish several journals, research papers on aquatic centers. So yeah, so let me go straight into the presentation. So today my presentation is about energy benchmarks and energy use simulation of aquatic centers. So I think those two topics are like two important steps if you want to make your aquatic center more energy efficient. Okay, just a bit of background of aquatic centers. So we all know that they are complex buildings, and they require a large amount of energy and water to operate. So the complexity comes from the interaction between air and water, which is the evaporation rate occurring within the swimming pool hole. So no other buildings experience that interaction. That's why it's so different from any other buildings, and there's not much research done onto aquatic centers. So as Jared mentioned, there's very limited studies on energy performance of aquatic center worldwide compared to any other types of building I've seen. So that's why I wanted to do that research, because looking into buildings, I could see there was a lack of studies done in that field. And the issue was because of evaporation rate, it's complex. No other buildings experience it. So my presentation today, it's mainly on benchmarking and energy modeling, and I will tell you why I think it's important and can get us to more energy efficient aquatic centers. So I think there's a very limited use of benchmarking here, even worldwide, when dealing with aquatic centers. So benchmarking your building is important, so you can measure, you can compare and understand the energy use of an aquatic center. So you need to know where it stands. And the other topic that I was going to talk about was actually using building simulation. This also, there's a lack of energy modeling software that can fully represent an aquatic center. So what this means, that can model the water evaporation interaction with the mechanical services. So that's the only way you're going to really represent what's happening in an aquatic center, by modeling that interaction. So benchmarking, energy benchmarking, why it's important. So benchmarking the energy performance of an aquatic center is instrumental to determine its current energy efficiency status and establish targets for improving its energy performance. What I mean by that, as I said before, you need to know where your aquatic center stands. You know, is it a typical energy consumption, when compared to other one, where does it stand? So if you don't know where it stands, how are you going to establish targets? How are you going to know what to look at? So you need to benchmark your aquatic center first, and then establish targets of what you want to achieve or what's possible. And to do that, you need a KPI, so a key performance indicator. So in buildings, there's two common indicators. Derek mentioned it. So it's energy usage intensity or energy use per unit area. And during my research, I found out that for swimming pool facility, there was the two most common EUR used. It was kilowatt hour per meter square using usable area, floor area, and kilowatt hour using water surface area, so swimming pool surface area. So what I proposed EUI for aquatic centers. So I did some very complex analysis during that research, and that indicated that condition usable floor area had the strongest correlation and significance to energy of aquatic center. But this is due because it's got both dry and wet surface. So you've got gym and fresh, you got it over dry facilities in aquatic center. So if for aquatic center, I think the EUR that you should be using, it's kilowatt hour per meter square using condition usable floor area. And then that was, as I said, it had a strong correlation to energy of aquatic center. And also benchmarking. So we came up with a unit to use, but also the research, we also came up with some benchmark. So we studied about 20 aquatic center in Victoria, and same using different variables and doing some analysis, we came up with a range of kilowatt hour. What we determine what's a low energy, medium, or high energy aquatic center. You will see in that graph here. It tells you, like below 1177 kilowatt hour, how it's considered as a low energy aquatic center, and so on. So, and also we found out that a typical aquatic center in Victoria was using around 1410 kilowatt hour per meter square. So as I said before, so that's a benchmark that's available now, and it's in Victoria. So if you benchmark your aquatic center, you'll be able to use that as a reference to see where you stand, and based on that, you can identify targets and work out, what next needs to be done. And so we've now we know where, the targets, we've identified targets, we have identified the benchmark. So there needs to be a tool to be able for you to measure, to see, how you can make improvement, and what improvement will make the best, or savings. So that's my next slide. So I found out during my research, and I wanted to come up with a target, and also to find ways on how to analyze your aquatic center to be able to work out, how to make improvement. So that's, I think, energy simulation. So nowadays, a lot of buildings now are using building simulation to analyze their energy performance. So it does provide a better, more accurate energy loads, and any building. So building simulation, it is a powerful tool, and it can be used to retrofit existing aquatic center, but also to design new ones, to be more energy efficient. So, and they're going to provide a bit more accurate energy loads compared to how we used to do it. I will explain it a bit clearer. So, building simulation, when I use my building simulation, we use a software. So that software, it's called Energy Plus. It's capable of modeling evaporation loads. So what this means is the software, like the swimming pool energy load, it's actually integrated into the surface heat balance of the software. So all the loads of a swimming pool, it's actually calculated in the software itself. So how it was done before, like evaporation loads and heat loss, evaporation heat loss, people used to calculate it manually using ASHRAE, like evaporation formulas. So like they were still simulating buildings, but they were adding that manual calculation as evaporating heat loads and heat gain as an internal heat loads into the simulation. So it didn't provide an accurate what I mean, it didn't provide an accurate environment of an aquatic center. So it didn't actually, because in an aquatic center, it's a dynamic environment. The air, the water is working not against each other, but you have to account for both of them. So that's why I think energy simulation can provide more accurate energy loads. So you will see those two drawings here. So they're actually an aquatic center that I model. So on the left, that's the envelope, and you will see on the right, you will see I'm actually modeling the swimming pool. There's actually 3 swimming pools inside that aquatic center. So it's actually modeled as it is. So there's no manual calculation. So everything is worked out by the simulation software. So using that methods, energy simulation, and using Energy Plus, you know there's so much information that's provided to you, and like for example the pie chart showed you can work out the energy and use by different the air heating, pool water heating, cooling, etc. But also what's more important, if you look on your right, it also gives you all the heat losses occurring in that swimming pool. So you will see how important evaporating heat loss calculation is, because on that graph, it's the highest heat loss in the aquatic center. So also with that simulation, you can come up with a bit more accurate heat loads calculation. You will see in that table, I've been able, that's just an example of the information that can be provided. So I've classified it monthly, but you can find any day of a year. Like it's just a dynamic simulation. So it's going to provide lots of information. You will see on the first column, the air heating energy. The other one is water heating energy. And I've put the other column to show you what it represents. So it's actually modeling the environment of an aquatic center. You can measure, you can see what's the relative humidity, and you can also see what's the temperature of the water, or even of a pool air temperature. So what this means is, so you can have a better heat load calculation. So you can see like what's the heat load required to get, for example, a lap pool to the temperature required, 29 degrees. So it does produce very important data that can be used now to make your energy use calculation of aquatics more accurate. There's one thing that I wanted to show you. I'll go back to my slide and to show you the importance of evaporation calculation. So you will see the evaporative heat loss to the pool. It's around maybe 30 megawatt hour. So in a year, it'd be approximately about 300 megawatt hour. Sorry. So when you compare that to the water heating energy, it's about one third of that water heating energy. So it does show that when you look at aquatic centers, you need to know about evaporation calculation and rate. Very important, because if it's just an add-on from your calculation, or you don't put, you just analyzing another building, you're not analyzing or an aquatic center, because that's the complexity. You need to understand its importance. So so that's the two-step that I think is important. So you benchmark it, and then use simulation to work out what's how you can make it more energy efficient.
Thank you, Jonathan. So, one more slide was there? Sorry, we're just a bit. We're over
there
time.
was one more slide. Yeah, just one quick slide. So one thing I wanted to clarify, like I've looked at many aquatic centers. So first of all, we need to analyze properly. You need to know where it stands, because if you were to change to a new system, that might have little effect on energy consumption. You need to know where the heat losses are. So, and second, your consultant need to have up-to-date knowledge on aquatic centers. They need to know the importance of evaporation calculation. You need to ask how they're analyzing energy use of aquatic center, what thermal simulation software they're using. Are they using manual calculation? So, in selecting design team, maybe we should select expert on the field instead of having one team that looks at everything, because not everyone's going to know expert at everything. Like, so for example, you might have an heat pump expert in that design team. I think we need to start choosing different experts based on their expertise, and also the use of appropriate simulation software. So so you can design retrofit aquatic centers. So yeah, so that's my presentation. So any questions?
Thanks very much for that, Jonathan. And we will maybe have time for one question. There was a question there about this software that you spoke of. Is that open source, and is there many consultants who are versed in this?
Yeah. So I've used Design Builder. So Design Builder is common in the building industry, but its engine that's used is Energy Plus. So what happened is I designed the building in using Design Builder, and then export it to Energy Plus. Energy Plus is free, so it's open source. So a lot of academic and it does simulate complex situations. So it is available. And in my PhD and all the papers that I've published, I did explain all the steps how to use it. So it is available out there, and there's information on it.
Oh, brilliant, brilliant. So if I'm hearing you, just before we take a short break, you've got a lot of these aquatic centers in this high EUI, sort of above 1600 or so kilowatt hours per meter square of conditioned space. But they could there's certainly surely methods and things to look at just to bring them down to that better energy performance, and that's certainly a worthwhile step before implementing a heat pump.
Yeah, correct. Yeah, correct.
Very
exactly.
Good. Okay. Well, since we do have the 2-hour webinar today, we thought it'd be appropriate just to have a quick 5-minute leg stretch. And so what we'll do that now, and we'll be back here at 3:40. Let me just share my screen so everyone knows what's going on, where we are. I'll get you to stop sharing there, or that's
Yep.
not there. Great, thanks, Jonathan. Feel free and type in some questions there for Jonathan. He'll be able to look at those and answer those in the live chat. We will have 5 or 10 minutes at the very end of the webinar to take some more questions. But I'd say, why don't we just take a quick 5-minute break. Back here at 3:40, top up that cuppa, and we'll get back into it and start looking at heat pumps and the sizing and the requirements for sizing of heat pumps when we get back at 3:40. So see you all shortly. Now we've got a good feel for the idea of comfort for the building and the modelling of the heat demand. We thought we'd now turn to looking at actual. Now we're sort of ready to size the heat pump. We've got a feel for this, and so joining us this afternoon we have Tony Kempton, who is I'd say a refrigeration and therefore heat pump expert. He's worked in this space for 35 years. He's now works in this. He's retired and likes to tell us about his vineyard, lovely vineyard at Mornington Peninsula, but otherwise he is helping with modelling of heat loads and heat sizing of heat pumps for aquatic centres, and doing a lot of consulting work generally for refrigeration engineering. Tony, great to have you here this afternoon and for you to share the great depth of experience you have with this technology. I'll get you to share your screen and run us through what we need to consider when we're looking at this heat pump technology.
Oops.
Yep.
There we are. Okay, so yes, I've semi-retired now, but I've spent my career building, designing and installing different types of heat pumps. So hopefully I can help some people out and give them some good information today. So today I'm going to try to explain to you a little bit about using heat pumps in aquatic centres. Hopefully you will soon understand a bit more about how the heat pump system works and how it differs from gas boiling heating systems, how heat pumps' capacity and efficiency are affected by temperature, why you would combine heating and cooling when using heat pumps, how heat pumps compare with gas boilers in energy consumption, operating costs and carbon emission, potential use of thermal storage, and if we get time, a discussion about refrigerants. Even though I assume that you're all aware of the basic operation of heat pumps, I'm going to start very simple. Two pipe heat pump has two pipes, warm water in and warmer water out. And when we're heating, all heat pumps also need to cool something. A two-pipe heat pump cools the air, so it uses air as its heat source. Four-pipe heat pumps have four pipes. As well as heating water, it is also cooling water at the same time. It uses water as the heat source, and this kind of heat pump is used when there is an alternative source of heat other than air available. There are also heat pumps available that can absorb heat from water and or air at the same time or independently. I'm sorry, I've just lost my notes. Okay, I'm flying blind anyway. All right, these are some examples of alternative heat sources. There's geothermal, sewage, ocean, river or exhaust air are some options. So there are some heat sources that you can get from the aquatic centre you have, maybe wastewater or that has some heat in it, or exhaust air. And these are three examples of aquatic centres in Christchurch in New Zealand. The first one from Pioneer uses the main potable water supply as a heat source during winter to take the heat out and supply heat to the pool. The Jelly Park Aquatic Centre, the middle one, is using artesian water as a heat source. And the Graham Condon Leisure Centre, all of these are in Christchurch, is using waste heat from the supermarket to assist heating the pool. So in New Zealand, they're far more advanced than we are in using heat pumps. And these sites, of course, are much colder than we would experience here in Melbourne. This is my first important slide that I want you to understand, and that is that capacity varies with temperature. It's not constant. So this is a slide of showing you that gas, no matter what day, what month, what season, is always the same capacity. A gas boiler has the same capacity, whereas a heat pump will have varying capacities. And so during winter, unfortunately, heat pumps have their least capacity. And then when the temperature gets warmer, they actually have more capacity. So in this particular example, I did some work for an aquatic centre in Melbourne, and they had 5 heat pumps. Well, the design had 5 heat pumps. So from this, you can see that for at least half of the year, only 1 or 2 of those heat pumps will be running, and the other 3 will just be sitting there standby. And then for 90% of the year, they'll be using 3 or less heat pumps. And only during the coldest months of the year will they'll need the last 2 heat pumps, with the final 5th heat pump only using or being needed when the temperature got below 5 degrees. This slide here is, I explained to you that the blue line is basically the heat pump capacity. You'll notice that as the temperature goes up, the heat pump capacity goes up. And the red line is actually the required capacity of an aquatic centre, or this particular aquatic centre. And of course, as the day gets warmer, less heat is lost from the building, and so for less capacity is needed. So this particular consultant was looking to design the heat pump system for an aquatic centre in Melbourne, and he chose the temperature of 3.5 degrees as the minimum temperature for that site. And he wanted 10% additional capacity, just in case capacity with the heat pumps at that point. So it just shows there that at 4.7 degrees, we had 20% more capacity than we needed. So at that point, that's when one of the heat pumps would shut off, one of the 5 heat pumps. But the main point was to discuss with the consultant at the time, wanted to put in some extra heat pump capacity so that he had an additional 600 kilowatts in case he needed to reheat one of the pools, or particularly the main pool, if it was shut down for some time or it needed to be refilled with water, and they wanted to get it heated quickly. He wanted an extra 600 kilowatts of capacity. And this curve just shows you that you only have to get to beyond 7 degrees in the ambient temperature, and you've got sufficient capacity there to do that. Okay, so this is a data sheet from a heat pump manufacturer. And you'll notice that he's got 2 columns of capacity. Capacity 1 is the heating capacity at 27 degree ambient temperature. And capacity 2 is the heating capacity at 10 degree ambient temperature. So you can see from the difference in capacity in the 2 columns that there is definitely a difference in capacity between the 2 different ambient temperatures. And if we look at the bottom, the biggest capacity, it's a 540, rated as a 540 kilowatt heat pump. At about 4 degrees in Melbourne, that'd only give you about 300 kilowatts. So this is why your heat pump doesn't work in winter, it's just not really big enough. So the second important piece of information I need to get across to you is that power in heat pumps varies with temperature difference. And I'll explain that to you. A split system is a type of heat pump. And so when we're using the split system, for example, to cool your building or office or house, and the temperature inside the room is staying constant, you'll know that, as we explained before, that if the source temperature remains the same, then the capacity will remain the same of the heat pump. So in this particular case, we're trying to push the cold outside, and so it's pumping against the temperature of the outside air. And we have 20 degrees going to 25, and it goes to 30. It uses more power on the power meter there, and up to 40. And what we're doing is pumping against that temperature. So the energy consumption varies with the temperature difference. And I'll explain that again, that the temperature difference between the air and the heating water in this particular case, well, in the heat pump case for aquatic centres. So with aquatic centres, we have this is just a standard heat pump that we could use in an aquatic centre, and you can see that the COP will differ from depending on the ambient temperature. And obviously, as it gets warmer, the efficiency improves, the COP improves, which again is similar to the capacity. During the coldest times when you need the most heat, it's at its least efficient. So given that I've just explained that the capacity, or the COP, sorry, of heat pumps differs depending on the ambient temperature, when we see data like this, it really has no meaning. There is no fixed COP of a heat pump, particularly when it's using air as a heat source. And so that has no relevance. Okay, I just completely repeating the same slide. This is another slide which I'm trying to explain that with an aquatic centre, when you're using a gas boiler, it's heating water to 80 degrees because that's what gas boilers do. And so a lot of engineers, or some engineers, may think that the best thing to do is to build a heat pump that's going to give you 80-degree water, and then everything else is just the same. But what I'm trying to show here is that if for example, you use water to 40 degrees to heat the pool, you're only making a temperature difference of 20 rather than 60, and your power is basically triple what it would be if you tried to heat the water to 80 degrees. Okay, so a 1 degree difference in heating water temperature can be equivalent to 2.5 to 3 additional power consumption. So just 1 degree difference in that heating water temperature makes a big difference to the overall power consumption of your heating system. So this is a typical example of what you might find in an aquatic centre, where you have the main pool at 28, kids pool at 30, and various pools at various temperatures. Always the spa is usually the hottest water that you need to heat. So if you're designing heating water to heat that series of temperatures, you'd have to make the heating water obviously hotter than the hottest water you need. And it only really needs to be 2 to 3 degrees higher than, say, the spa temperature in this case. So 39-degree heating water would be adequate. But what my point is here is that if you didn't have the spa there, you wouldn't need to have 39-degree water. You could do it with 33-degree water, and that would be enough to heat your whole aquatic centre. And as I explained before in the previous slide, with 2.5 to 3% per degree difference, we're looking at about a 15% additional energy consumption of the whole heating system of the whole aquatic centre, just because you have a spa. So we need to think about not everything when we're talking about using heat pumps in an aquatic centre, how we're designing everything associated with that. Now, I've lost all my notes, so I'm flying a little bit blind, but there's 3 things that, other than maybe the initial cost, that people ask me about when we're talking about aquatic centre heat pumps: energy consumption, carbon emission, and operating costs. So the carbon emission from electricity today is about 5 times more than burning gas for energy. And that's because in Victoria, this is Victoria. So in Victoria, the electrical energy is quite dirty at the moment. So if you wanted to build an aquatic centre today that was able to give you less carbon emission than using a gas boiler, you would need to have a COP of about 5. Now that's possible, but no aquatic centre built today would have had that COP yet. But luckily we have the government has actually some future reductions in its, or improvements in its power supply, and the overall efficiency you'll need over the lifetime of a heat pump, if you put one in today, would only need to be a COP of 2 to be better than a gas boiler in a heating situation. And a COP of 2 is quite easily achieved. It's most heat pump systems would do better than that over its life. So energy cost is a bit different again. At the moment, the cost of electricity is about 3 times the cost of gas. And obviously that is likely to become more beneficial for electricity in the future. But that only means that you probably need to design an aquatic centre or a retrofit to have at least a COP, an average COP of 3. Now, when I say average COP, you understand that it's going to be different. It's going to be lower in winter and higher in summer. I explained that. So it is very complicated to try and work out what that average would be, because you use more energy in winter at the time when the COP is its lowest, and you use less energy in summer when it's at its highest. And then, of course, if you're combining heating and cooling, the average COP becomes a very difficult task to try and calculate. But that's the number you should be aiming for. Okay, the red line is the heating demand of a typical aquatic centre. Obviously, it's low in summer, you don't need that much heat, and then during winter you need the maximum amount of heat, and it tails off again. The cooling demand for an aquatic centre, which would have a typical aquatic centre, which would have gyms and active spaces, well, its maximum cooling demand would be in summer, when it have virtually 0 through winter. And there are times in summer where the cooling demand would be more than the heating demand. Okay, so if we combine heating and cooling together and using both of them with a heat pump, then we can effectively say that we're getting free cooling. So any cooling that's supplied from the heat pump, we can consider really free. So the green areas in this curve, or shaded in areas, are explaining where we can get free cooling in a typical aquatic centre. Now, in summer, when you've got more cooling than you have heating, you basically need to waste that heat. It has to be wasted into the atmosphere. And that's what the blue sections are there. But then during most of the cooler months, you have way more cooling wasted than you need. Sorry, you don't have any need for cooling really, and so most of that cooling is just wasted. Okay, now I'm going to talk to you about refrigerants. Yeah, I'm assuming I still have some time. And everything I was going to say to you was on notes. I haven't got it here, but what I will say is that of the synthetic refrigerants, they started with CFCs, and as you know, they've been eliminated now. They went to a version of refrigerant called an HCFC, which was also no longer used. And then the next synthetic refrigerant that was invented was HFCs. Now, it's been discovered that that's not a very good option either. And throughout most of the world, they've been also eliminated or they've been banned. In Australia, they've decided to phase down HFCs, and it's been in place since 2018. And the concept is that the government wanted to give everyone time to change their system to another refrigerant while the units that were installed still had life left. So rather than pull them all out and throw them away, they're giving everyone time to change them. But what's happening is people are still installing new systems now with HFCs. It's not really working. There are loopholes in what the government has to try and eliminate HFCs, and people are getting around them. But that'll change. If it's not with this government, it'll be with the next. But so eventually HFCs won't be used in Australia. And most of the councils now have policies not to use HFCs, and it really is they just shouldn't be used. Okay, this is going to be tough without my notes, but I'll try and explain. You might have seen pictures like this before in the days of CFCs where they showed the ozone holes in the atmosphere. So this is a curve showing you the amounts of HFOs that are in the atmosphere. Now, HFOs are the next version of synthetic refrigerants after HFCs. So that's pretty much the ones that people are using now. But what happens with HFOs is in the atmosphere, they break down into PFAs. Now, if you've ever heard of them before, they were used as fire retardant chemicals that you hear about now, that people are jumping up and down about, and how it's polluting the ground and that sort of thing. So PFAs as a substance is banned now in a lot of countries. You can't use it anymore in fire retardants, and it's also been used in treating clothing and carpets and things like that. But it's highly expected that eventually HFOs, because of what they're doing and how they're releasing PFAs into the atmosphere and then eventually leaching into the ground with rain, that they may also follow the same path as a lot of the other synthetic refrigerants that have gone before them. So at the moment, in Australia and in most of the rest of the world, HFOs are still available and still being used, but it's just something to have in mind. So that pretty much leaves just natural refrigerants. Now, CO2 as a refrigerant for heating aquatic centres is a particularly poorly efficient heat pump type. They're great for heating hot water for HWS or for your shower water. I have one here in my house for heating my hot water. They're great for that, but they're not ideal for heating hot water for heat pump systems in aquatic centres. So that leaves us with ammonia and hydrocarbon. Ammonia has been around for a long time. It's used in many applications for heating and cooling. It does have its problems with toxicity and flammability, but obviously there's regulations around how to use it and how to safely use it. And the same can be said with hydrocarbons. It is obviously flammable, but if used correctly, it can be used safely. Okay, now I think I went a lot quicker than I expected, Jared, because I lost all my notes. But happy to answer any questions, and hopefully I got to the end okay.
Thanks, Tony. No, went over, but it was good.
Oh, did it?
I couldn't stop you. It's really good to hear about these refrigerants. I couldn't stop that. It's a really important point to be made there. And so, yeah, it's almost like the industry does need to find a way to work with ammonia or hydrocarbons. And they come with their own challenges, but certainly not insurmountable. So, but many thanks for that, Tony. We'll consider one question just before we move on to our final speaker, and that's about this sizing of pipes and well, also heat exchangers. As we go from 80 degrees of the heating hot water loop, taking that down to 40 degrees or so. Yes, the heat exchangers, I think I'm okay to comment on that one. The heat exchangers will need to get bigger as you have those closer approach temperatures, but adding plates to a plate heat exchanger is what they're designed to do. And so that's not an issue.
My pleasure.
In terms of thanks, Siri, in terms of the pumping there, the pipes and what have you, understand if you're putting VSDs in them, you can adjust it, and maybe only for certain very peak loads, you've got much higher pressure drops. What's your thoughts on that one? Have you done much in the way of modelling of how that's going to impact pipe sizes and things?
Yeah, of course. If you're retrofitting, you'll need obviously bigger heat exchangers, probably bigger pumps and bigger pipes as well. So it's not just a matter of taking out your boilers and putting in a heat pump. There's a lot of other componentry that needs to be changed as well if you're putting in a heat pump system. So, but in the end, the cost of replacing the heat exchangers or making them larger is peanuts compared to the amount of energy you're going to save and the cost of the energy that you'll be putting back in. It will pay for itself in no time, in less than a year for a lot of the heat exchangers. So it's not even worth considering anything else, really.
Perfect. Thank you so much, Tony. A really good overview of those key design elements, and I think it's really important for people to understand that when they're specifying this, they can make sure they get something that's future-proof and it's going to get the best results overall. So many thanks for that, Tony. I'd like to move back to our first speaker that joined us now, and Chris Warris is going to kick the discussion home for our final speaker today. And we're just going to loop back and talk a little bit more about the economics of the boiler versus the heat pump, and dive into these VEECs that are available through Victoria as a way to reduce that in the cost and be rewarded for saving those carbon emissions. Chris, I've got your screen shared up there. If you could come off mute and put that into presentation mode, and away we go.
Okay, here we go. Hopefully that's happening.
And meanwhile, if there's some questions there for Tony, feel free to pop that in the chat. We'll probably have 5 or so minutes at the end to take them. But yeah, feel free for a bit of a side chat there with Tony, and go for it. Chris, thank you.
Yeah, I just need to move this now. Yeah.
All right.
Okay. So thanks, everyone. I'll just talk a little bit about Northwell Gordon. We're an energy and carbon consultancy. We work with large energy using organisations to reduce their energy costs and decarbonise. The advantage of going last is that I get to listen to what everyone else has said, but also the disadvantage is that some of my thunder gets stolen. So I'll skip through some of this that we've already been talking about. But we've mentioned this before, and sort of this reiterates what other people have said. But if you're looking to replace your gas boilers, you can do the like-for-like capacity replacement, which is going to be expensive, long capital. Much better to correctly size it. Use heat recovery if you can, and combine it with energy efficiency and get a really good result. So don't do the like-for-like replacement. If nothing else, just size it correctly. Even if you're just looking at the heat pump only, you'll get a decent payback. And then ideally do a more integrated design. So my key messages, and the key messages that everyone has said, is really key to size that heat pump correctly. The existing boilers are often oversized, and you need to understand your actual heat demands. So either by measuring your actual heat demand, or modeling it using a good model. And this is particularly important for, so it's not just the pool heating. You know, you've got pool heating, you've got air heating, and you've got domestic hot water heating for your showers, and they all need to be sized correctly. Use waste heat from your facility if you can. The previous speaker talked about improving the COP, or the efficiency of the heat pump, by reducing that temperature difference. Makes a big difference. I'll talk about gas prices in a moment, and energy efficiency certificates. So just, this is another version of similar diagram that other presenters have talked about, but you've got in your aquatic centre, you're losing a whole bunch of heat from the pools in various ways. Most of it is through evaporation from the hot pool water. So you need some sort of heating system to replace that heat. So if you've got an existing gas boiler that's burning gas, you're losing some heat immediately out of the exhaust of that gas boiler, and then that heat goes into the pool or into the aquatic centre, and then is lost in the various ways. So the simplest way is just to replace that gas boiler with a heat pump that's the same size. So if we look at an example of an aquatic centre with a 922 kilowatt gas boiler, which is this is a medium-sized aquatic centre. It's got 700 kilowatts of installed capacity for the pool and air heating, and it's got 222 kilowatts of installed capacity for the amenities hot water, and that's enough to provide continuous hot water for 14 showers. The gas use in this facility is 7,889 gigajoules per annum, and it costs them nearly $100,000 a year at $12 a gigajoule. The gas price is about to rise, so obviously with a high gas price, those costs are higher. With a heat pump, so you do a like-for-like replacement of the same size, and that would cost for 922 kilowatts of heat pumps, it would cost somewhere in the order of $900,000. So it would reduce, or it would eliminate the gas use, but it would consume its own electricity to do the same heating. And if you look at the numbers, there is a cost saving there. If you're looking at $12 a gigajoule of gas and 12 cents a kilowatt of electricity, which is typical prices that we've seen up till about a year ago. So cost saving, there is a cost saving there, but it's a 28-year payback. The payback does improve with the higher gas price, but you're still looking at a long payback for doing something like this. But when you look at the data for this facility, they actually only need 410 kilowatts for pool and air heating. That's actually the maximum heat consumption that it uses. And on the domestic hot water side, they've got enough capacity there to provide hot water for the 14 showers running continuously 24 hours a day. Now, they obviously don't use that much hot water. They can actually get away with a much smaller capacity, but with a large hot water storage to get them through those peaks. Because they have a peak in the morning where, you know, most of those showers would be used. Maybe 80% of the showers are used for, you know, 80% of that hour. And then it's much lower usage throughout the day. And then they would have another peak in the afternoon where they would need a bit more of that storage. And then overnight, it's not using any hot water in the showers. So the heating system could recharge the storage overnight. You get away with a much smaller heating system then. So they actually only need about 440 or 450 kilowatts of heat pumps. So that's pretty much half the price, $450,000. So they've halved the capital cost by just sizing it correctly and using some hot water storage. Now you're getting it down to a 14-year payback, and it becomes a 5-year payback if you look at $20 a gigajoule gas. Now, all of that heat that's being put into the pool and that you're replacing with your heating system, if it's just leaving the facility, going out to atmosphere, then you just need to keep putting it back in again. But if you can capture some of that heat and reuse it, or use it in your heat pump to make it work better, you can put a smaller heat pump in and it will work more efficiently. So now they only need 310 kilowatts for the pool and air heating, and the heat pump cost goes down to $350,000. This may or may not be practical depending on how much modification you need to do to enable that heat recovery. In some cases, it can be relatively inexpensive, but in some cases it can be very expensive and potentially impractical. But in some cases, it can be done. Now you're getting it down to a less than 7-year payback and a 3-year payback with $20 a gigajoule gas. So heat pumps de-risk you from high and volatile energy prices or gas prices. So if you look at a sensitivity analysis on energy prices for that previous example, just using the right sized equipment, not using the heat recovery or anything fancy, we're looking at that $450,000 capital cost, and at $12 a gigajoule gas and 12 cents a kilowatt of electricity, that was around here. So the payback, the payback was here at around 14 years. I'm just trying to move my things there. So, but you can see that it's very, very sensitive to the relative gas and electricity prices. So this is where we have been in previous years on gas. So you're looking at high paybacks for heat pump. But at the moment, the gas price is about $40 a gigajoule. So you can see as you approach those high gas prices, the payback really drops to that sort of 2 to 3 year number. And I mean, who knows what gas prices are going to do in the future? I do have some indications on the right here. This is the ACCC's LNG netback price. So this is some sort of forecast of what gas prices are likely to do. It's not exactly what they will do, but it's sort of the best forecast that we've got. And you can see that even out 2 years from now, they're not predicting gas prices to be coming back down to where they used to be. It's well above $30 a gigajoule out as far as the forecast goes. So if you were to go out today and get a new gas contract, if your gas contract is coming up for renewal at the end of the year, you'll be very lucky to get anything in the 20s. It's most likely going to be in the $30 a gigajoule for a gas contract. And if you're looking at $30 a gigajoule for gas, it really doesn't matter what your electricity price is going to be. The heat pump business case and payback is going to be very good. Now, electricity prices can be volatile too, but if you can get rid of gas, now you only have electricity to worry about, and you can de-risk your price volatility there by installing on-site solar PV to fix that price for whatever you can produce on site. And then with the renewable electricity power purchase agreement, you can fix your electricity price long-term as well. So just de-risk yourself from volatile gas prices. And the final thing I'm going to talk about is just the main source of funding that you might be able to get for these sorts of projects is using the Victorian Energy Upgrades program. So this is a legislated program in Victoria where one Victorian Energy Certificate, or VEC, is equivalent to 1 tonne of carbon dioxide abated for your project. The current price for VECs is about $70. There are a couple of different methods, but for a large aquatic centre, you'd be looking at a measurement and verification method, this is where you measure your energy consumption prior to doing some upgrades, and then measure it afterwards, adjust it for various differences in operation, and calculate the savings against that baseline period, and create certificates, or VECs, according to those savings. So VECs can be created by accredited persons, such as Northmore Gordon. So if we look at a case study for a Victorian aquatic centre, using our example from earlier, replacing a gas boiler with a correctly sized heat pump or heat pumps, installing 400 kilowatts of solar PV on the roof, and that would produce about the same amount of electricity over the year as is used by the new heat pumps. Do some energy efficiency improvements to reduce your electricity use. So that might be some BMS optimizations, pool pump controls, building fabric improvements for better insulation. Just to get an extra 10%, you would be able to create 5,650 VECs, and that would be more than $300,000 of net revenue to your project. And you would get that money 12 to 18 months after the implementation, because you have to measure for at least 12 months after you do the upgrade before you can create the certificates. So that can have a really significant impact on the business case as well. So yes, summary of the key messages: size the heat pump correctly, use waste heat, de-risk from gas prices, and access VECs. Brilliant.
Thanks, Chris. I think you've shown us how you can really move the needle there in the economics a lot. So that's great. And hopefully that helps everyone there. Chris, I still hear people talking about solar thermal and using their roof space for solar thermal. Any thoughts on that? I'm not seeing much go ahead on that. Just hearing questions about it. Any thoughts on solar thermal and how that plays in?
Yeah, I did actually see a question in the chat that was also answered on similar lines, Jared. But look, I think 10, 15 years ago, solar thermal we were looking at it, it was a good option. But since then, the price of solar PV has really plummeted. Solar thermal hasn't really changed as much. So now it's almost always better to just use that roof space with solar PV and then use the electricity generated from it to, drive your heat pump, drive other things in the facility. The business case is better. Use that roof space with solar PV rather than solar thermal. The other problem with solar thermal is that obviously it doesn't really give you much in winter, so you still need some other sort of heating system anyway. See solar thermal used a lot in a lot of regional councils that aren't open all year round. So all it does is just extend their season a little bit, and that's a cheap way of extending the season. But if you want to be open all year round and maintain your pool in winter, the solar thermal is not really going to do it.
Very good. Thanks very much for that, Chris. A quick comment came through there on the idea of PVT, so solar PV and and thermal combined, where you recover heat from the back, essentially the back of the solar PV. Now, I understand that's being implemented at a site in North Sydney as part of their upgrade. So I guess we'll watch and see how that goes and the practicalities of that one. But yeah, probably something to watch. It might be a nice little adder there to boost your source temperature. And going back from what Tony was telling us, every extra degree is going to give you that 2.5–3% boost in your performance. So yeah, one to watch there. Great.
And it would make the solar PV work a little bit better, because solar PV is more efficient at lower temperatures too. So
cool.
it all comes back to how much that costs to do.
We'll have to watch that one. There is a couple of companies that are promoting that. I think it's Cool Sense and Sonovate over in WA. So we'll watch how they go with those ones. Good. There is a question on the footprint there. I think that's a really important one to address before I just wrap up with a bit of O&M. Anyone care to comment? Maybe that one's there for you, Tony Kimpton, to talk about the footprint required for a heat pump, say, versus an existing installation, existing site for a retrofit.
Most heat pumps in Victoria are probably going to be using air, at least partly, as a source. So they need to be, the heat pumps themselves need to be outside, or at least part of them needs to be outside. So that'll take up roof space, or you can put it on the ground next to the main building. So as far as how much space it's going to take up, it also depends on how much capacity you need for your aquatic centre. But generally, you probably won't be using your existing area that you have for your gas boilers. It won't be sufficient to put it all in. Plus, you need to put it outside anyway. So it has to have more space, more area to put it in.
I've heard about something like around about a sea container or so sized for that. Maybe a 1 megawatt heat pump, and yeah, that could be actually
probably two size containers for that.
The 40-foot or it's big.
No, probably two 40-footers. Yeah,
40-foot for that one.
Yeah, I mean, depends on the type of heat pump you're talking about and the cost. The more you spend, the bigger it gets. Funnily enough.
And certainly a lot looking at the roof-mounted ones as well. At least having those the evaporator coils, having them on the roof for sure.
I'd make a comment as well. Like I can see Rod Kington from City of Sydney. We've done a couple of projects with him, and yes, definitely finding space for heat pumps can be an issue in a retrofit. Yeah, as Tony said, you can't put it in the same plant room. You've got to find somewhere else to put it. And we have seen sites try and jam heat pumps into a corner somewhere, and that's problematic because the heat pumps need airflow across them so the cold can be removed. So you need to be careful not trying to jam it into a small spot. It does need to be somewhere where it can get good airflow. Otherwise, it won't work very well.
And consider noise implications of moving outside. It's another one to keep in mind.
Yeah,
absolutely.
Otherwise, you'll be forced to turn it off at night. Yes,
you want to be well below 50 decibels if you want to run in the evening. I'd say closer to 40 would be nice. Eh? Very good. There was comments that came through in the registration poll about operations and maintenance. It was a little bit difficult to answer, but let me try. We did a fair bit of investigations. Certainly, there is many heat pumps out there, air conditioners and what have you. Really, really well-known technology in that respect. For aquatic centres, if you go to New South Wales, many heat pumps have been in there for a long time, but people move around, and we noticed that we on investigating, not many had good data. So we have a series of anecdotal feedbacks here, and certainly the one from North Sydney Council was clear that look, they've had heat pumps for 20 years there, and they're definitely using them again in their redevelopment project now, but they saw that after about 10 years, they saw the maintenance costs starting to creep up a little bit, and after after 15 years a few more issues, but certainly it did last the 20 years that they needed them for to get them through to that redevelopment. And their expectation is when you start looking at ammonia type heat pumps, you know, the lifespan is more likely 20 to 50 years. And anyone who works in that refrigeration space with ammonia heat pumps, you'll see they are often around for well over 20 years. And we'll get Tony Kimpton started on that one. I'm sure he's got some old stories for very old units there. The other one was Inner West Council. They implemented a heat pump for their Ashfield site some 2.5 years ago. They have had a few maintenance issues they sort of put down to COVID, but they're certainly working through those and don't see it as a major issue. They're for their next two upgrades, they're certainly looking at heat pumps there. So there's nothing too bad for the technology to take it out for them. They're still going ahead. I can share one with the Parramatta Memorial Pool, personal evidence and eyewitness of that one icing up on the cool days there. That system was obviously poorly designed for the defrost systems and what have you. And so they, right when they needed it most, they did see some operational issues there of the machines icing up. So whether they didn't have the right defrost functions, but clearly something was wrong with the designs that they had in that one. The other one to mention is someone like Logan City Council, who has ammonia systems for their buildings, but doing the chilling and the heating. Their costs there, and they've had them in for quite some years, are seeing around about $11,000 per year for 2 systems. And I think that's coming out to a 0.5 to 1% of that capital cost or so. So you can see it's really quite economical, and you would expect it far below your costs for your combined heat and power. And it's certainly likely to be lower than your boiler maintenance costs as well. So there's still plenty of lessons to learn on operations and maintenance, and we've got this sort of next generation of heat pumps coming through as we look at the natural refrigerants, and so this does require that feedback and that knowledge sharing to work out the best ways to handle this. Just have a quick look. I had a few more things to share with you all. There is a new publication coming out very soon that DELP, we have ourselves worked with DELP on heat pumps, and a bit of a guide for you. And it gets into a little bit more technical detail than what we did today, and will help you run through that. And it's got some case studies and more detail there for heat pumps as well. And so that should be out within a matter of days or most weeks of that one, and that should be a really good resource to help you with some guidance there as well. If you wanted to go back and have a look at some more and dive deeper about heat pumps, there's lots of webinars that we've got on our website. If you go to a2ep.org.au and go through events, you'll see half a dozen or so webinars posted there, and a couple specifically on aquatic centres. So you could, if you want to go back to look at heat pump basics and review that, or you want to look at the story behind Brimbank and their decision making, there's the videos on there as well. Plenty of case studies as well we've put together for you. If you go to futureheat.info, you'll see a series of different case studies on heat pumps, not just for aquatic centres, but others as well. And it's got the very good one down there at Hobart, where they're using waste heat. I think that's from sewerage, or at least sort of a district heating type system, where they're recovering it from wastewater. And so that one there is a really good case of how you can find a great waste heat source to improve the performance there. So with that, look, a few more bits and pieces, and you will get this on the slides, and you'll get the links there when this is emailed out to you. But there is a few other resources there if you want to dive a little bit deeper as well. But I think that might do us for today. We're getting very much close to the end. I did have a Slido questionnaire for everybody, but we won't go through that, unfortunately. Just let me have a quick look over the questions there and see if we can answer anything in the last minute or two before we close out. And if there was anyone who wanted to come off mute and ask a question, we've got maybe a minute or so if we just go a little bit over. There was a comment about geothermal, or we could call that Well, geothermal, or maybe say ground source, if we included that as well. Geothermal, I think if you're in the right location, the well itself is quite expensive, but I think it's worth investigating. I don't know if anyone has actually done that investigation in Victoria just yet, but I think it'd be worthwhile taking that, and you'd get a similar result probably to a ground source design or heat pump. Otherwise, look, I think that might have to do us. There was a question on reheating the pool, and I think that was answered. We had a great community responding there today, so thank you for those, for how fast you can reheat the pool. And I think someone mentioned about it's limited by the pool and not wanting to crack them in terms of that heating and what have you. But yeah, certainly that would have to be part of the modelling consideration. And if you're taking your pool down every couple of years for the reconditioning, does that mean with a heat pump solution you need to have the pool closed for just 1 or 2 days extra? Otherwise, it may cost you another $1 million. Or do you need to rent some sort of a temporary heat pump solution just for those couple of days? That sort of things would have to be considered for sure. Look, I don't want to go too much over. We are over time.
Jared, just a quick one.
Yes,
did you
please.
mention $1 per kilowatt additional cost of heat pump versus boilers at the start, and what was that figure?
Yes, so usual numbers you'd be looking at is for a boiler somewhere around about, I usually use $80,000, $80,000 to $100,000 per megawatt. And then for a heat pump, you'd be, call it $800,000 to $1 million installed. That's typically installed. Always lots of ifs and buts come with that. If you had to upgrade your electrical system and you're a transformer or something, that will go higher. But in theory, if you follow the path we went through today, you won't need to do that. If you're putting on solar PV, if you're optimizing the building design and optimizing the heat pump design, in theory, you won't need to do that electrical upgrade. But if you do, that can be substantial. But let's call it 80 to 100,000 per megawatt for the boiler, and then maybe a little bit more for installation there. But yeah, call it 800,000 to $1 million per megawatt for a heat pump.
So approximately 10 times, but you wouldn't need to go the same size if you potentially you might not need to go.
So you may say 10 times, but I'd say more likely 3 to 5 times.
Yeah.
Because the heat pump, and if you do it correctly, should be so much smaller than that thermal capacity you had for the boiler. Thanks for the question. Glad to have been able to clarify. Okay. Did go over. We usually finish on time, so apologies for going over today. I would like to thank Sustainability Victoria for bringing this together, and really hope it's a great resource for aquatic centres across Victoria and to wider aquatic centres as well. I would like to thank our speakers today, Chris Warris, Noy Hildebrand, Derek Harbison, Jonathan Duverge, and Tony Kimpton. Many thanks for the effort put in there for today, and I think you've given everybody a great resource to refer to, and really hope that works for everybody. So we'll have the slides and recording out to you as soon as we can. I'd say at the very latest early next week, and you'll have that on YouTube, and you'll have the slides, and so this should be a great resource for you. So all that's left to do is say wish you all a very nice afternoon, and thank you for joining us. Well, hello again, everyone. We've got a few more questions that have come through on the chats, and Chris Warris from Northmore Gordon has agreed to stay on and help me answer these. Chris, the first one we've got is on the pipe sizing, and that relates to right now you may have a hot water boiler sending 80-degree hot water to the main heat exchangers to heat up the different pools and what have you. If we lower that temperature, say down to 40 or 45 degrees, that may necessitate a higher flow rate and a larger pipe sizing there. Any thoughts on how to go about that one, Chris?
Yeah, I look at that. That is likely to be required. As Jared says, it's going to be a different temperature coming off the heat pump, so you will need to change likely need to change that primary hot water piping and heat exchangers, and maybe the hot water pumps as well. But look, that's sort of part of the costings that we've talked about in the webinar. Kind of includes the whole installed cost. typically the heat pump itself is only, half or 2/3 of the installed cost, because you do have to do some of those additional upgrades, but that's included in the numbers we've used.
Gotcha.
So, but yes, it's a good point. It does have to be considered.
So I guess you would hope that the heat pumps are going to be located pretty close to where those heat exchangers are, and therefore that those larger pipe sizes can be reduced. Let's hope. Other comment coming through, and I think this is well phrased, to say right now we are looking at this from an engineering perspective and get the size right and what have you, but at the end, this is people dealing with the public here, and if these pieces of equipment aren't performing, the centre managers are going to see some complaints if the heat pumps aren't doing their job. How do we go about that to making sure that's not going to happen?
Yeah, look, I mean, when we say, downsize the heating plant, we're not advocating to put not enough heating in. It's just you still need to put enough heat pump capacity in to be able to to be able to keep the pool at the required temperature. So that absolutely has to be achieved. So you have to size it to be able to do that. It's just that what we find is that gas boilers are often, because they're cheap, they're oversized. So there's often significant extra capacity, much more than you actually need, just because it doesn't cost much more to put that extra capacity in. So you just can't afford to do that with heat pumps. You just have to accept that you're going to have to reduce your safety factor in the heat pump design, but still being able to achieve the set points that you want.
Indeed, and it's a case most of the people on the webinar here are going to be going through a retrofit, and that is usually much more expensive than if you just did heat pumps straight from a greenfield. However, it does come with one advantage, and that's that you can map that heating requirement more accurately. So again, let's go back to our 1 megawatt boiler case. If you were to map that the actual demand on that boiler through winter, you might see that the maximum you ever draw, it could be 750 kilowatts. You go, okay, well now I know what size to make my heat pump. I don't need to get that 1 megawatt. I'm going to go for 750 kilowatts right there. So there's that one advantage of retrofit where you can have that payoff. Yeah. Next comment we have there is about disruption when it comes to retrofitting a heat pump. If I had to change out a boiler, like for like, pretty quick, I'm probably doing that in a matter of days. Or let's say I had to take the pool down for a complete empty and reconditioning, what have you. Am I going to see a longer time to bring the pool up to speed using a heat pump? First one, that change out for going, instead of just a boiler, adding the heat pump?
Yeah, look, I mean, it might be a little bit more disruptive, but shouldn't be significantly more. I mean, again, it's just putting in a new heating plant. You can get the heat pump in while the boiler's still running. You can place it on the roof, get it all ready to go, and then the disruption comes in just connecting the new pipework to the heat pump and your pool. So look, it's not it's something that needs to be planned, but it's not a significantly bigger job than replacing a boiler. And the second question around refilling the pool after emptying it with a heat pump, well, it really depends on the time of year that you do it. As one of our speakers talked about, with the the heat pump capacity being lower in cold conditions, if you're trying to refill your pool in the middle of winter, the heat pump's going to take a long time because it's at its reduced capacity. But if you can do it in autumn, one of the shoulder seasons, then there should be more than enough capacity for the heat pump to do it just as quick as a boiler.
I guess autumn might be the best time then, when you say that the fresh water, the town water coming in, is still going to be warm from summer.
Exactly.
Because if you did it in spring, that water could be coming down 5 degrees and you probably have 20-30% more heating to do because it's coming in much cooler. So there's certainly ways around it. But if we're talking an extra day or so for making that heating with the heat pump, I'm sure that's still going to be a worthwhile exercise and not going to blow out of the water any sort of cost benefit or return on investment. Good one. Also see here in the chat, actually, we've got some really good comments here about other electrified pools, someone already in Victoria going ahead with heat pumps that we weren't aware of. So great to see that Merbau North has gone ahead with heat pumps, and I see that from the case there, it looks like that's been running now for maybe 12 months. There's in Bendigo, we've got the Peter Krenz Aquatic Centre. Someone's put in the chat there, and also there's the Bright Aquatic Centre. Looks like they've all gone electric. So Chris, some more for there to watch and more for us to find out how they're going and do the knowledge sharing on that one.
And look, and there's no doubt there's going to be more and more in the future. So yeah, it'd be good to be part of it.
Brilliant. All right, and that looks like it's gone through most of the main questions and themes that we've got coming through on the chat. So we'll leave it there, and that will conclude the webinar. Many thanks again for joining us.